In this video, we're going to look at how we can graph the position of an object as it moves over time. And we call this graph a position versus time graph. So we have position versus time. All right, and the variables we use for position, we use x for a horizontal location or position, we use t for time. So we'll often refer to this as an x versus t graph. So really we can look at where an object is located, its position, as it moves in time. Now there's a couple things that we're going to look at that's going to really inform how we analyze the motion of an object. The most important thing to look at in a position time graph is the slope of the function or the lines. Right? So if we're calculating slope in math class, it would be the rise over the run, which if we're looking at this graph, that would be the change in position over the change in time. So we're looking at position time graphs. Slope is a critical idea. And the slope would be the change in position over the change in time. And if you recall, that is the definition of velocity. So when we're dealing with slope on a position time graph, we're really looking at the velocity of the object. And keeping in mind, velocity is speed and direction. Right, so but with that velocity, we can tell which way it's going and how fast it's going. So if we see that the line on the graph is a straight line, then we know that the slope is not changing. So we want to look at our graph, and if we identify any straight lines, then we know we have constant slope. That is what a straight line would be on this graph. And a constant slope would indicate that the velocity is constant. So that would be constant velocity, meaning that object is maintaining its speed and direction. All right, so we call that constant velocity. However, we've now learned about this idea of changing velocity, also called acceleration. So if we see that the graph, and we see some spots in this graph where we see curved lines, curved lines would indicate changing slope. Slope of the lines are changing if it's curved. And again, if slope is velocity and we're changing our slope, then we have a changing velocity. So it's really just telling you what is happening to that object over time. If it's curving, then that object's velocity is changing. And changing velocity is also called acceleration. And we'll dig a little deeper into acceleration here in a little bit. All right, so not only do we need to identify whether the slope is constant or changing to see if it's constant velocity or accelerating, but now we can look at the steepness of the slope. Right, we call that the slope's value, right? So not only do we see the slope, but we can look at the value of the slope. The slope value, also known as the amount or the magnitude. Magnitude is just a fancy word for amount. The value of the slope, or the magnitude, or the steepness, how steep the line is, would also be an indication of its value. All of these things are indications of the speed of the object. All right, so how steep it is how fast it's going. If you think of the speedometer on a car, whether you're going east or west, doesn't matter. How fast it is the slope. All right, so if I'm looking on a graph and I see a slope that's up and to the right, we would say that that is a positive slope. And that indicates that that object is moving in the positive direction. All right, so let's say this is positive 3 meters per second. There might be a value associated with that amount of slope. This object is likely moving to the right, which is usually what we assign the positive direction. On the flip side, you might have another spot on that line where you have a slope, something like this. And you might calculate its value to be negative 3 meters per second. It's a negative slope. Negative slopes typically refer to objects moving to the left, right, as what we might define as the negative direction. The important thing is both of these slopes have the same magnitude. They are the same speed. The steepness of the slopes aren't different. They are both 3 meters per second. However, one's positive, one's negative, so we know they are different directions. So if we can identify the steepness and also whether it's positive or negative, we can determine the direction of that object. Now, sometimes you get curves. So let's look what happens when we get a curved slope, right? So we get curved slopes, curved lines. Again, we have changing slopes, and which means we are changing our velocity. So let's look at an object that might have a curve that looks like this. This object does not have a constant slope, right? Its slope is changing. And what we can do is we can look at the slope at any given point. We call that a tangent line. So at this point, there might be a slope that's really steep, right? Let's give it a value. Let's say it's positive 6, right? Might be the value. And it's going to depend on how we actually are measuring certain things. But it's going to be a positive slope. And at this point, we have high speed. It's steep. So this object is moving fast at this point. It is also moving in the positive direction. As it moves along, though, the slope at any given point flattens out. We get less and less slope, right? The little tangent lines that we can draw, maybe you have, let's say it's positive 4 right here, then positive 3, then positive 2, all the way down to maybe 0, right? And we would say that up here we have low speed, small slope. So even though it's curving, right, we can identify the slope at any given point, right? So this object, if you see a curve in this way, we know it's moving. All the slopes are positive, which means it's moving in the positive direction. However, the amount of slope is decreasing, right? The slope is becoming more shallow. Slope is decreasing. Which is an indication that we are slowing down. And we are subtracting velocity, right? So we are taking away velocity, which would indicate it has a negative acceleration. It is slowing down, right? It is subtracting velocity, which is what a negative acceleration would do. Now, another way you can slow down, well, what if I move it in the negative direction? Well, we could get a slope, a curve that looks like this. This is also an object that is slowing down. And the way we know that is it goes from steep, which means fast, to a slope later that is shallow. Shallow would be slow, right? So we're looking at the amount of slope at these given points, right? So what would it look like if we're speeding up? Well, you would see something that looks like this, an object starting flat and speeding up. Or you might start fast this way, or start slow at the top and speed up this way. Both of these are speeding up. The slope is increasing. But remember, these are actually in different directions, right? This would be in the positive direction. All these slopes are positive. And this is the negative direction. So we can indicate which way the object is moving. All right, so this is a basic summary here to indicate how we would interpret these lines. Now, let's take a minute and just look back at this original graph here, and we'll kind of identify a couple key points in this graph of what's happening to this object. All right, so when we look at this motion sensor, the motion sensor measures things out in front, so we know that the positive direction is going to be away from the sensor. Let's look from point A to point B. Well, from point A to point B, we have a slope of 0, and therefore 0 meters per second. It is at rest. The location after 2 seconds at B, it is still located at positive 1 meters. However, what happens from B to C? Well, from B to C, the slope is flat at B and then steeper at C. So the velocity is increasing. This is a spot that is speeding up. So between B and C, we are speeding up. Now, between C and D, we have constant slope, right? So this would be constant velocity. Constant speed or velocity. And so would be right here. Those are both flat, constant slopes. And in fact, the amount of slope from G to H, I would go down 3 units and over 1. This is a velocity of -3 meters per second. And from C to D, we would go up 3 and over 1. This is +3 meters per second, which means we actually have the same speeds between C and D and G and H, but different directions. At the top, once again, we are stopped. We have no slope and therefore no velocity. And from H to I, our slope becomes shallower, and so we would be slowing down. And lastly, we move at constant speed from I to J, right? And it has a velocity. We would go down 1 over 5. This would have a velocity of -1/5 meters per second, which we would typically write as 0.2 meters per second, negative, right? And overall, we have an object moving away from the sensor and then back to the sensor, right? So the overall motion of this cart, you would see all your positive slopes from here to here is an object moving to the right. Then it sits stationary for 1 second from 6 to 7. And then from this point, from F all the way to that 15-second mark, you start getting negative slopes, which means we are moving left or towards the sensor, if you want to say left is towards the sensor, right? So here we are just kind of breaking down a position time graph, an object starting at the 1 meter mark away from the sensor, sitting stationary, speeding up, holding their speed for a second, slowing back down, stopping at the 6 meter mark, going back towards the sensor now to G, holding its velocity, slowing down again, and then finishing right at the sensor. And in this case, it has velocity to actually run right into the sensor. It doesn't stop at the sensor. So hopefully this gives you a pretty good example of how we would analyze a position time graph for an object that is moving in multiple directions at multiple speeds, speeding up, slowing down, holding constant velocity, all of which we can determine by analyzing the slopes of the graph along the line over time.